In SAS, we can perform the Cox proportional hazards model using Phreg. The SAS program will look somewhat similar to what we've seen before with proc live test. Here you notice that there is a class statement which includes treatment. This is not necessary. However, it's nice to always include the variables, the categorical variables in a class statement, so you can decide which reference you want. In this case, we want 1 to be the reference. 1 was the standard treatment. We then write the model in a similar way as we've seen before. We have the outcome that is made of 2 variables, the duration and the status. 0 indicates the censored observation, and the predictor is treatment to the right side of the equal sign. We request confidence intervals for the hazard ratio with the option RL. And this is a way of handling ties using the Epi-Lon method. And you don't have to worry too much about that right now. We're stratifying on Reno, as you have seen before. We want to include Reno as a nuisance variable, also because we don't have a large sample size. In the output, because we've entered treatment as a class in the class statement, we will see this box appear. What SAS does in the background is that it changes the coding for treatment from 1.2 to 0.1. However, what's most important is that we will see here the number 2, which will tell us that treatment 2 is compared to treatment 1. We will also see another box for the overall p-value. And we will see that the score test here is the p-value is 0.0161. As you recall, this is the exact same p-value that we found in proc live test for the log rank test. Then we also see additional output, which is the hazard ratio and the confidence interval. This can be interpreted as that the hazard for treatment 2, which was the new drug, is 4.32 times higher compared to the standard treatments after stratifying on renal function. We can also check the proportional hazards assumption. Here you can see the code that we can use to check the proportional hazard assumption for the variable treat. And at the bottom right of the slide, you see the LLS plot, which shows that the lines are crossing, suggesting that the proportional hazard assumption is violated. There are ways to address this. For example, if the sample size had been larger, we could have included an interaction between treatment and time in proc Phreg. So how do we interpret the hazard ratio? The hazard ratio interpretation is very similar to the interpretation of an odds ratio. It's a measure of the effect of an exposure on an outcome. In this case, it was the exposure was in the intervention, the exposure to the drug, and the outcome was death. So we concluded that the hazard for those receiving treatment 2 was 4.32 times higher than the hazard of those receiving treatment 1. This hazard was proportional, was the same regardless of time. So if the hazard ratio is greater than 1, the exposure increases the hazard of the outcome. If the hazard ratio is less than 1, the exposure decreases the hazard of the outcome. In this case, the exposure was treatment 2, was the new drug, and the hazard ratio was greater than 1. So the new drug increased the hazard of death. It was not a good drug. With a larger sample size, we could have also included renal as a covariate in the model, as you can see here. And this is the output. You can see that we have now two variables, treat and renal. We may be interested in the effect of treat after adjusting for renal, and the odds ratio and confidence interval is shown here. The variable renal could also be assessed, but in this case you can see that the confidence interval is very large. It goes from 6.98 to 744.73. And that's why it's probably not a good idea in this case to include the renal as a covariate. Note that the hazard ratio is the parameter estimate beta exponentiated. So for example, the hazard ratio of 3.396 is generated by exponentiating the parameter estimate 1.22.